afternoon and welcome to the Museum of Science Live. Today we are going to be doing a virtual planetarium show exploring the universe. It's Space Month here at the Museum of Science and all around the world, and we are going to be talking today about some great topics involving the universe and mysteries that we are still beginning to unfold. Now, I have two educators here from the Museum of Science who are going to be helping us out today with some awesome presentations. Before I ask them to introduce themselves, I'm going to let everybody who's watching know that if you are joining us on Zoom, feel free to submit any questions you have through the Q&A chat, as well as any observations that you might have during our broadcast. For those of you joining us through Facebook and YouTube, we are so glad that you are joining us. We can't see the comments that you type, but we are so glad that you're participating nevertheless. Now, at this point, I'm going to ask our two educators to introduce themselves.
Hello, everybody. My name is Talia. I use she, her pronouns, and I am going to be doing most of the talking today, but I cannot do this alone. I need help.
Hi, everyone. My name is Katie. My pronouns are she and her, and today I will be providing the visuals for the program. So I will mute my camera so you can see those visuals.
Thank you so much. And now I'm going to turn my camera off and hand it over to Talia.
All right. And if we can also spotlight Katie's video so that everybody can see what she is showcasing. So last week, Katie talked a bit about dark energy. We don't know what it is, but it is helping to fuel the expansion of the universe somehow. So today we're going to talk a little bit about that expansion of the universe getting bigger, and how we measure it, and how those measurements lead to a little thing that I like to call the Hubble Wars. So for a very long time, people assumed that the universe was static, that it didn't get any bigger and it didn't get any smaller. It was not moving. In fact, in 1915, when Albert Einstein published his theory of general relativity, he actually made alterations to it because his equations suggested that the universe was changing size. And he was like, well, that can't be true. So he added an extra term onto his equations just to make it so that the equations would say that the universe held still, because it was so strongly assumed that that's what was going on. Then in 1929, so 14 years after Einstein published his general relativity equations, Edwin Hubble, who is a person whose name we're going to be hearing a lot today, he confirmed that the universe is in fact expanding. And he did this by confirming the findings of two previous astronomers who had looked at their findings and said, it kind of looks like these things are moving away from us. That would suggest things are expanding, things are getting bigger. So Hubble was not the first one to raise that, but he is the one whose findings, he looked at his findings and went, oh yeah, no, the universe is expanding for sure. And that's why, even though he wasn't the first, he is the one that got the law named after him. So this idea that the universe is expanding is what we call Hubble's law. And it's not just that the universe is expanding, it's that it is expanding faster the farther away things are from us. So things that are relatively close to us seem like they're moving at one speed away from us, and things that are farther seem like they're moving at a much faster speed away from us. That's what Hubble's law states. So once he knew that the universe was expanding, Hubble wanted to be able to measure it. And to do that, he came up with a kind of convoluted unit of measurement. So we're going to take a moment right now and talk about this weird unit of measurement that he came up with. It's called kilometers per second per megaparsec. And what that basically means is a unit of speed, kilometers per second, over distance, megaparsec. And so that is saying that, speed increases the farther away something is, that things are moving away faster the farther away they are from us. They're just using units that we don't tend to use in day-to-day life. We often actually talk about speed in terms of miles per hour, not kilometers per second. But they're both units of speed. They're both a distance over a time. Miles per hour uses miles and hours. Kilometers per second is just substituting kilometers in place of the miles and seconds in place of the hours. And that is a pretty standard unit for scientists to use, is kilometers per second. Now, megaparsec, that one's a little bit weird. That is not a unit that gets used very often, and really nobody outside of astronomers uses it. You may have heard the term parsecs from Star Wars. Han Solo claims that the Millennium Falcon can do the Kessel Run in less than 12 parsecs, which makes it sound like it's a unit of time. It is, in fact, a unit of distance. And I'm not going to go into the whole origin of where that specific unit of distance comes from, because that's a whole nother rabbit hole. But a parsec is 3.26 light years. 1 parsec is 3.26 light years. So the nearest star to us is about 1.25 parsecs away, the nearest star to the sun. A megaparsec is 1 million parsecs, so 3.26 million light years. And that's a pretty big distance. To give you an idea, our nearest big neighbor, the Andromeda Galaxy, the nearest big neighbor galaxy to the Milky Way, is less than a megaparsec away from us. It's something like 2/3 of a megaparsec away from us. So that's a pretty big distance. So when we're talking about the rate that the universe is expanding, these are the units we're using: kilometers per second per megaparsec. And since Hubble really was the first to make this measurement, he came up with a measurement of 500 kilometers per second per megaparsec. This rate of expansion, the rate of expansion of the universe, got named after him. So he already has a law named after him, right? He's already got Hubble's law. Now there's a constant named after him, the Hubble Constant, or H0. The H with the little 0 gets pronounced H0. And this is what we mean. This is that number, that rate of universal expansion as measured in kilometers per second per megaparsec. And he came up with a number of 500. That is what he thought the Hubble constant was. He was completely wrong. Very, 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 very wrong. That's not terribly surprising. Again, he was making this measurement back in 1929. He had relatively rudimentary instruments for measuring distances to things, which is a huge part of figuring out what the Hubble constant is. And today that is no longer the case. But I think before we go into what we use to measure today and what those measurements tell us, I know I threw kind of a lot of crazy units at you. So Sarah, have any questions come in that I should answer before we move on to clarify or anything like that?
I think today the only question that we have so far came in before we started and is asking us about the exploration of exoplanets. I'm not sure if they mean the topic or actually going to the planet, but maybe you could just let people know sort of where in the scale of things do exoplanets fall compared to what we're talking about
so far, most of the exoplanets we've found out in space, their distance can be measured in parsecs. So not megaparsecs, just parsecs, because all of the ones that we have discovered are inside our own Milky Way. And our own Milky Way is far, 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 far less than a megaparsec. I think our Milky Way is about 50-ish parsecs across. The whole Milky Way is about 50 parsecs across. So a parsec is a pretty big unit of distance, which means a megaparsec is a really big unit. All right, so Hubble, Edwin Hubble, makes his measurement, decides that the universe is expanding at the rate of 500 kilometers per second per megaparsec. He is, of course, completely wrong. He didn't know that at the time. He was working with, again, the sort of detection instruments that they had in the 1920s and 30s. And of course, as time has gone on, not only have our instruments gotten a lot better at telling us what we want to know, So our instruments are far better. We've also come up with many different ways to measure what H naught is, what that Hubble constant is. So for instance, we can look at measurements from very, very early, from very, very, very far away from us, which means very early in the universe's history. Like this. This is the cosmic microwave background. This is the radiation that's left over from the Big Bang, which means this is this is from the very beginning of the universe. And one thing we can do is measure little fluctuations in this background radiation using telescopes like WMAP, which is the Wilson Microwave Anisotropic Probe. We just call it WMAP, or Planck. And both of these spacecraft stared at nothing but this background radiation. So we can use their data to measure tiny fluctuations in that background radiation. Or we can use things like the Sloan Digital Sky Survey to measure the density of visible matter in the early universe. And those are two ways that we can come up with a measurement for the Hubble constant, for how fast the universe is expanding. And those are both measurements from really early in the universe's history. So we're taking those measurements from very far away. Then there are other things we can measure that are a little bit closer to home. And by that, I mean within a few billion light years. That's what I mean when I say close to home. And these are things like type 1a supernova, which this is what you're seeing is a model of a type 1a supernova when the remains of two sun-like stars that have actually died or out of fuel, they're now white dwarfs. Sometimes they mash together and they create a new kind of supernova. So that's one thing we can measure. Another thing is called a Cepheid Variable. It's a type of star that changes brightness on a very known scale. Basically, both of these things are things where we know the brightness is to a pretty high degree of precision. We know how bright they are. And if you know how bright something is, then you can guess how far away it is based on how bright it looks. If you know how bright a flashlight is, because you just know how bright it is, then when you see it in the distance, you can sort of guess how far away it is based on how dim it looks. Like if you know it's a really dim flashlight and you can still see it, it can't be that far away, for instance. So we can look at those things that are really far in the distance, way back from the beginning of the universe, or we can look at things closer to home within a few billion light years, which means they've happened much more recently. And this is the second thing. This is, we use telescopes like the Hubble Space Telescope because Edwin Hubble got so many things named after him. So the Hubble Space Telescope or the Gaia Space Telescope have been very, very integral to making these sort of closer in measurements for how fast the universe is expanding. And today's measurements are far more accurate. So what this is a graph of the values for H naught, for the Hubble constant that we've measured since Hubble first started measuring it in the 1920s, all the way up to today. And you can see his first measurements were way different from what we're getting today. We're closing in on those values. You can see they're getting much closer together. And that's because they're much, much, much more accurate today than they were back in Edwin Hubble's day. And those very accurate measurements are leading to an interesting problem. And this is what I like to call, nobody else calls it this, I like to call it the Hubble Wars. So here's the issue. Our very, very, very accurate measurements don't agree with each other. If you look at the measurements we've taken more recently, so this is since the year 2000s, and those dots sort of show the primary measurement. The bars on the other side are the error bars. The smaller those are, the more confident we are in the measurement, essentially. So smaller error bars are better. So what we seem to have are two very, very accurate and very different values for H naught that keep appearing depending on how we're measuring it. The Hubble constant is supposed to be a constant. It's supposed to be the same everywhere. That's what being a constant means. But when we make measurements based on the things relatively nearby, like the Cepheid variables or the type 1a supernovas, we get a value of around 73.5 kilometers per second per megaparsec. So right around there, where that line is. You'll notice that's way less than the 500 that Edwin Hubble thought it was. But here's the thing. When we make measurements based on things that are really far away, things like the cosmic microwave background, at the very, very edge of the visible universe, we get a value of around 67.7. Now, if you look at these, a lot of these have very, very low error bars, very short error bars. And that means that we're fairly confident in the measurement, or we think we are. So here's the thing, 73.5 does not equal 67.7. These are not, or 67.4 rather, these are not the same number. If the Hubble constant is in fact a constant, the way we think it is, the way we always assumed it was, these numbers should be the same. And they're not. They're certainly a lot closer to each other than the number of 500 that Edwin Hubble started out with, but neither of these matches. And what's more, we know both of them to a fairly high degree of accuracy, which means, you know, back in the days when we were far less certain, those big error bars would overlap with each other and we could be like, all right, so the real measurement's somewhere in between. But now we don't have that. We have two sets of very accurate measurements that don't agree with each other. And what's more, I had this talk all outlined last week, and then more data came in, which made the picture even more complicated, which really gets to the fact that this is an ongoing source of confusion for astronomers who study the universe at large, cosmologists, as we call them. There's a new way of measuring H0, a new way of measuring that expansion rate of the universe. This one is based on red giants. So based on studying stars like the sun, which are at the very end of their lives and have swelled up into giant red stars. And this new measurement gives a value of 69.8, right smack in the middle. So here's the question, what is going on? We have all three of these measurements to a fairly high degree of accuracy, and they don't agree with each other. Basically, a couple of things could be happening here. Science depends on using measurements to draw conclusions about how the universe works. When the measurements no longer support the conclusion, you basically have to say either the measurements were not made correctly, or the conclusion, the thing we thought we knew about the way the universe worked, is incorrect. So what's the question? What's the case here? Are we looking at bad measurements, or are we looking at a bad understanding of how the universe works? We don't know. Scientists, astronomers have been starting to come around to the idea that maybe the Hubble constant was not actually a constant. Maybe the rate of the universe's expansion has changed over time. Maybe it was slower in the past and it's increasing now. And you know, this was something that people were starting to come around to because there were these two measurements that were so very accurate, but so very different from each other. Now, just this past week, there's been another sort of shift. Again, this is all an ongoing saga that has been changing even up to this last week. And what's happened this week is that they're now raising the question of maybe we're measuring those close by things, the Cepheid variables, maybe we're measuring them wrong. Maybe we've been measuring them wrong this whole time. Maybe that 73.5 is a completely wrong number. Even though we thought we had it to a very high degree of accuracy, maybe we don't. We're going to have to figure it out. So we have sort of two different explanations at play here, different cosmologists favoring different ones. One of them says that the measurement's wrong, says that we've been measuring this incorrectly, and therefore it's giving us bad conclusions. Another is saying our conclusion was wrong. What we thought about the universe, that the Hubble constant was a constant, maybe that is not the case. In this particular case, maybe the universe is behaving in a completely different way than we thought it is, which would actually be really cool if that turned out to be true. So we're not sure what's going on. I don't have the answer for you, I'm afraid. I wish I did. So either we don't understand the universe quite the way we think we do, or we don't understand Cepheid variable stars quite the way we think we do. It's probably one of those two. Right now, we don't have the means to answer that question, but we're working on it. We've got the next generation of space telescopes that is going to play a big role in trying to answer this question, try to fill in the gaps with what we know, try to make sure that we actually do understand what's going on with the universe, or that we don't, but we can figure it out. And in the meantime, the universe keeps expanding at one rate or another. Again, we don't quite know how fast. And it's going to continue to, thanks to dark energy, which is another thing we don't understand. Once you start talking about how the universe as a whole works and fits together and operates, there's a lot of gaps in what we know. And that's why the upcoming generation of space telescopes is so important. It's going to help us fill a lot of those gaps. So this was a very weird topic, the expansion of the universe and how astronomers are fighting over what that value is. Sarah, are there any questions about what we've talked about today?
Yeah, we have some great questions here. So first up, a question from Regina. What are some other explanations about how the universe operates? And if the numbers or measurements are wrong, how would the correct measurements be found? So two great questions there.
Those are great questions. So one of the things we think might be wrong is, like I said, we're measuring the Cepheid variables wrong. That means we think maybe what we've done is the assumption that we had about how accurately we knew how bright these Cepheid variables were, that could be incorrect, which would mean we've been measuring the distances to them incorrectly. And then we use those Cepheid variables basically to figure out how far away the type 1a supernovas are. So if we got the incorrect measurements for one, we got the incorrect measurements for the other. And those are the things we're really, the nearby things that we're relying on to get that 73.5 measurement. So one of the things we could do to fix that is to figure out if, in fact, get a better understanding of the behavior of these variables, these Cepheid variables, to really determine, do we understand them to the degree that we think we do? And that's one thing that the Webb and Roman telescopes are really going to help us with. In terms of what else could be going on, who knows? I mean, like, we used to assume, like I said, that the universe was static. And then we assumed that it was expanding, but that expansion was going to slow down and everything was then going to come together in a big crunch. Now we know it's not. It's expanding and it's expanding and it's expanding. So every time we learn more, our view of how the universe is behaving is changing. We think we have a pretty good handle on it now, but maybe we don't. Maybe it's another thing that's going to change the way we look at how space moves and changes over time. To be continued.
Great answer, thank you. And sort of along the lines, thinking about these new next generation telescopes, Ashley asks, is the James Webb Hubble's replacement, and has the backup system on Hubble kicked in yet?
Both excellent questions. So James Webb often gets touted as the replacement for Hubble, but it can't really replace Hubble because they look in different types of light. Hubble looks in visible light and a little bit in ultraviolet and infrared. Webb is only going to look in the infrared. So Webb is going to be able to see farther than Hubble. So in that case, it's sort of like the next generation, the successor to Hubble, and that Hubble so far is the thing that's seen the farthest, and Webb is going to surpass it. But they look in different types of light, which means Webb can't really replace Hubble. As for Hubble's backup, last I heard, they had a pretty good handle on what they think the problem is, and they have an outline for how they're going to go about solving it. It's something that they're going to do slowly, testing every step of the way, because obviously Hubble is a precious resource and we want it to recover from this little hiccup it's going through right now. So as of right now, Hubble is still offline, but they have a plan.
And then we have a question here from Rishik, who asks, how will this expansion impact Earth? So I'll go ahead and sort of expound on that a little bit, that, you know, is the Earth getting farther from the sun, from the moon, from Neptune? What's going on with this expansion?
That is a great question. And the good news is that it's really not affecting Earth at all. The space that is expanding is not the space within galaxies. It's not even the space between galaxies very close together. So for instance, Andromeda and the Milky Way are getting closer. But galaxies live in clusters. They live in groups. And it is the clusters that are getting farther apart. So everything in the Milky Way is not getting farther from anything else in the Milky Way. Everything in our local group, the cluster that the Milky Way is part of, is not getting farther away. Like I said, Andromeda and Milky Way are actually getting closer. But outside the local group, the other clusters of galaxies that we see, they're expanding away from us, and they're expanding away from each other as well. So the clusters of galaxies, the space in between these clusters of galaxies is expanding. Within the clusters, gravity really is keeping everything from moving apart.
All right, and I think for now that is our last question. So I can ask our two educators to say goodbye.
Thank you, everybody. Your questions were great. I know this was a weird topic. Thank you so much for letting me talk about it, because I had a fun time.
And with that brings us to the end of our presentation here. So we want to thank you so much for joining us here today. This was made possible thanks to help from NASA with a NASA grant. And so we highly encourage you to keep on exploring all of this. A lot of this information, especially those images, is publicly available. It belongs to NASA. So you can check out eyes.nasa.gov if you're interested in doing more space exploration with those amazing telescope eyes in the sky. So we encourage you to come back and join us for next week's virtual planetarium presentation right here, same place, same time. Thank you so much. And please enjoy your virtual or in-person visit to the Museum of Science.